Students, welcome to s.mathguru classes. Now we consider Euler's theorem. We solve some problems about Euler's theorem. Now we have some formula by using Euler's theorem. If z is a homogeneous function of degree n, so that x del square z del x square plus y del square z del x del y equal to n minus 1 del z del x, and number 2, x del square z del x del y plus y del square z del y square equal to n minus 1 del z del y, and this one x square del square z del x square 2xy del square z del x del y square del square z del y square equal to n into n minus 1 into z. These three problems we have to solve. Now initially given z is a homogeneous function of degree n. Solution: since z is a homogeneous function of degree n, therefore by Euler's theorem we have x del z del x plus y del z del y equal to degree into function. This is number one we consider. By Euler's theorem, already the derivation it was given in the first video. X del z del x plus y del z del y equal to degree into function. Z is a function and degree is n. Now first we want to find this one. This one means del square z del x square given. So we differentiate partially with respect to x. Differentiating 1 partially with respect to x, we get del x, this is x del x plus y is constant, this is outside del x del z del y, and this is n del z del x we get. This one we get. And this is product of two function. This is first function del x of second plus second function del x of first. First function del x of second and del x, second function del x of x, and this one y constant del square z del x del y n del z del x. We get this one, and this will be x, this is x del square z del x square, and this is del z del x into 1 del x 1 plus y del square z del x del y n del z del x. And taking this del z del x on right hand side, we get x del square z del x square y del square z del x del y, this is n del z del x minus del z del x. Just taking this on right hand side, we get this, and this implies x del square z del x square y del square z del x del y del z del x common z minus 1 n minus 1 del z del x. We get this first one. First proof we get. So this is our first proof. So I want to write the result here. X, not x, x del square z del x square plus y del square z del x del y n minus 1 del z del x. This is number 2 we consider. First one is done. Next we have to find second one. Second one we get del y square. First one we get del x square, so we differentiating partially with respect to x of 1. Again we differentiate partially with respect to y of equation 1. So we differentiate this partially with respect to y. Differentiating number 2 we consider differentiating 1 partially with respect to y. We get, so what we get, we have del y square, so we multiplying by differentiating with respect to y. So del y x del z del x del y y del z del y and del z del y. So x is constant because we differentiate partially with respect to y. X outside del y del z del x. This is product of two function. First function del y del z del y plus del z del y del y del y n del z del y. We get this. And this implies x del square z del y del x, and this is y del square z del y square del z del y into 1. Del y 1, and this is n del z del y. This implies x, we can interchange this del z del x del y, and this is y del square z del y square, and this one taking on right hand side n del z del y del z del y, taking on right hand side we get this, and this implies x del square z del x del y y del square z del y square equal to n minus 1 del z del y. This is the second proof. Second one we get. Second result we get. So I want to write the result here. This is x del square z del x del y, and y del square z del y square equal to n minus 1 del z del y. Number 3 you consider. Just we get two proofs, this and this. Next our requirement this. Now our requirement this proof. But in this problem, so here we get x square, xy, y square. So if we multiplying this equation by x, then we get x square del square z del x square. This term we get. This one we get. And again, if we multiplying this equation by y, then xy, y square del square del square. This term also, we also get. So we multiplying this equation by x and this equation by y, and adding we get. Now 2 into x plus 3 into y. We multiplying equation number 2 by x and 3 by y, we get x. First multiplying this equation by x square del square z del x square xy del square z del x del y plus this one y multiplying by y xy del square z del x del y plus y square del square z del y square equal to, on right hand side we multiplying by x and this is y, n minus 1 x del z del x plus n minus 1 y del z del y. Just we multiplying equation number 2 by x both sides and 3 by y and adding, we get this. So this implies x square del square z del x square, these two are like terms, we can write 2xy del square z del x del y, and this is y square del square z del y square, and taking n minus 1 common. If we taking n minus 1 common, we get x del z del x plus y del z del y. From these two, n minus 1 common, then we get this. But we know this value. By Euler's theorem, this value is x del z del x, y del z del y, nz equal to, this equal to nz. So this will be n minus 1 nz using 1. Finally, we get, therefore, x square del square z del x square 2xy del square z del x del y, y square del square z del y square equal to n into n minus 1 into z. This is the third proof. Hence, short. These are the complete proof. This is nothing, very easy solution. So dear students, so this type of formula is very important, and when you have to solve some problem by using this formula, this is problem also but formula also. When you have to solve some problem using this formula, we get our answer. So I hope you are all enjoying with me. If you are all enjoying, then please like this video. If you are new in my channel, then please subscribe my channel and click the bell icon. Thank you.